Yes, hello everyone. So good morning. Yes, so for the past 7 to 8 videos, we are seeing previous year solutions of UPSC Mathematics Optional Paper 1 Linear Algebra, right? So we have only completed 2017 to 2024 in the previous classes. So in this video, we will solve 2016 paper of Linear Algebra. So in this paper, there are 9 questions. One question has many subdivisions, so that it has 9 questions, but it has 70 marks only, right? So overall, 70 marks from Linear Algebra, 9 questions, but all 9 questions are very, very good questions, right? You will learn many things from these 9 questions, right? Okay. So we'll start our first question. So we'll start, right? Everything is clear, audio and video. Okay. So we'll start our first question. Using elementary row operation, find the inverse of the matrix A, which is given by 1 2 1, 1 3 2, 1 0 1. So this carries 6 marks. Actually, this has some. It will take time to do this, but they have asked only for a 6 mark. But we will do this, right? So we need to find the inverse of the matrix using elementary row operation, not by using the formula, that is 1 by determinant of A into adjoint of A. We have to find the inverse of the matrix using elementary row operation, that we will do by Gauss-Jordan method, right? So we will make use of Gauss-Jordan method to find the inverse of the matrix. Okay. So what Gauss-Jordan method was said? Jordan method what says is, if you want to find the inverse of the matrix by elementary row operation, you do the following thing. The first thing is you write the matrix A with ID matrix of order 3, because A is a 3 cross 3 matrix here. So we have, what is A here? So A is 1 2 1, 1 3 2, 1 3 2, 1 1 0 1. Then you write an identity matrix, right? You write an identity matrix, which is 1 0 0 0 1 0 0 0 1. Now what you have to do is, you need to make this matrix as ID matrix, and whatever the operation that you are doing to make this matrix as ID matrix, make the same operations here also. I'll repeat. I think this video is clear, right? Or it is zoomed in, correct? Or it is, I think it is zoomed in. Okay, so I'll do it with zoomed in, I think. Okay, so no problem. So we'll do this. So using elementary row operation, find the inverse of A. So what you have to do is, you have to make this matrix as ID matrix, right? You make this matrix as ID matrix with the help of elementary row operation. Whatever the operation that you are doing to make this matrix as ID matrix, the operation you follow here also. After making this as ID matrix, this matrix will be some other matrix. So this matrix will be called as inverse of that matrix, right? So I'll do this. So first we have to make this matrix as ID matrix. So the step one is make this element as, I'll write on the steps also. Step one is write, make, step one is make A11 is equal to 1. Make A11 as 1. Just a minute. So make A11 as 1, and make these two elements 0, and make A21 and A31 as 0 with A11, right, with the help of A11. We are reducing the ID matrix, right? We are making first row, first element 1, and below that everything is 0. Now already this element is 1, so we don't need to make this as 1. Suppose if it is some 2, you divide by 2, that R1 row, so that will be 1, right? So already it is 1. So make A11 as 1 and make A21, A31 as 0 with the help of A11. So already A11 is 1. So we'll make these two elements as 0 with the help of A11. So what we'll do is, we will make a transformation. R2 is transformed to R2 minus R1. R3 is transformed to R3 minus R1. I'm making these two 0. With the help of A11. So the thing is, this operation I'm applying here, I have to apply here also. So the new matrix will be 1, 2, 1. So 1 minus 1 is 0. 3 minus 2 is 1. 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 2 is minus 2. 1 minus 1 is 0. Now you have to apply the same operations here also. So R2 minus R1. So 0 minus 1 is minus 1. 1 minus 0. 0 minus 0. So 0 minus 1. And then here we have 0 minus 0. Here we have 1 minus 0. Right? See, our first column turns out to be the first column of ID matrix, right? 1 0 0. Now the second step is make A22 as 1 and make these two elements 0, right? And make A12, that is first row, second column, and third row, second column as 0 with the help of A22. Already our A22 is 0, right? So sorry, 1. Already our A22 is 1, so we don't need to make that as 1. Suppose if it is 3 or 4, you divide by that number throughout that row. So we see that already this is 1. Now we need to make this element 0, this element 0 with the help of A22. So what we'll do? So we need to make this element as 0. So R1 is transformed to R1 minus 2 times R1. Yes or no? So you multiply 2 here and then you subtract. And this R3 is transformed to R3 plus 2 times R2. This is 2 times R2. Yes or no? I need to make this element 0. I need to make this 2 as 0. So I need to make this 2 as 0 and minus 2 as 0 with the help of 1. So you multiply 2 here and then you subtract. You multiply 2 here and then you add. So these two operations will make these elements 0, this element as 0. So apply the same operation here also now. So our new matrix is given by 1 0 0 1 2 1. Now R1, sorry, R1 is transformed to R1 minus 2 times R2. So 1 minus 2 times 0 will be 1. 2 minus 2 times 1, this is 0. 1 minus 2 times 1. So 1 minus 2 is minus 1. Is this step is clear? Okay. R2 will remain as it is. So 0, 1, 1. Now R3 is transformed to R3 plus 2 times R2. So you multiply 2 and then you add. Right? You multiply 2 and then you add. You multiply 2 and then you add. So it will be 2. Right? Now you apply the same operation here also. R1 minus 2 times R2. So 1 minus 2 times minus 1. So 1 plus 2, it will be 3. 0 minus 2 times 1, which is minus 2. 0 minus 2 times 0 is 0. R2 will remain as it is. Minus 1, 1, 0. Right? Minus 1, 1, 0. Now R3 is R3 plus 2 times R2. R3 plus 2 times R2. So minus 1 minus 2, which is minus 3. 0 plus 2 times 1, which is 2. 1. Right? Now you can see our second column turns out to be the second column of identity matrix. Right? Second column of identity matrix. Now what is our step 3 now? Step 3 is make A33 is equal to 1. That is, this element as 0, sorry, 1, and these two elements as 0. So make A33 is equal to 1 and make this is A13 and A23 as 0 with the help of A33. So we need to make this element as 1 first. So we'll make that element as 1. So for that I will do R3 is transformed to, I'm dividing R3 by 2, so that this will be 1. So here you can see already A22 is 1. Already A11 is 1. So I'm not doing anything. Suppose if there is some other number other than 1, you divide by that number throughout the row. So this becomes 1 0 minus 1 0 1 1. I'm dividing by 2. So 0 0 1. So this is 3 minus 2 0 minus 1 1 0. You divide by through 2 out. Minus 3 by 2, 2 by 2 is 1, and this is 1 by 2. Now we have maken A33 as 1. So now we will make this element 0, this element 0 with the help of this. So that means R1 is transformed to R1 plus R3, and R2 is transformed to R2 minus R3. Because we need to make this two elements 0 with the help of this element. That is Gauss-Jordan method. So this is equivalent to 1 0. Sorry. Now R1 plus R3. 1 plus 0 is 1. 0 plus 0 is 0. Minus 1 plus 1 is 0. Right? Minus 1 plus 1 is 0. R2 is R2 minus R3. So 0 minus 0. 1 minus 0. 1 minus 1 0. R3 will remain as it is. Right? Now you have to apply the same operation here also. R1 plus R3. So what is 3 minus 3 by 2? R1 plus R3. So 3 minus 3 by 2. 6 minus 3 by 2. So we have 3 plus 3 by 2. So which is 9 by 2, right? 3, okay, 3 minus 3 by 2, sorry. 3 minus 3 by 2. So which is 3 by 2. So this number is 3 by 2. And then we are just adding R1 plus R3. Minus 2 plus 1 is minus 1. 0 plus 1 by 2 is 1 by 2. R2 minus R3. So minus 1 plus 3 by 2. Minus 1 plus 3 by 2 is minus 2 plus 3. This is 1 by 2. Right? Minus 1 plus 3 by 2. So 1 by 2. R2 minus R3. So 1 minus 1 is 0. This is 0 minus 1 by 2. And this will remain as it is. Minus 3 by 2. 1 1 by 2. This step is clear. So we can see that we have made this matrix as the left hand matrix as an ID matrix, right? So we have got this matrix to be 3 by 2 minus 1 1 by 2, 1 by 2 0 minus 1 by 2, minus 3 by 2 1 1 by 2. So this is our inverse for the matrix. This is Gauss-Jordan method. This matrix is given by A inverse, right? So thing is you have to write A comma I3. You have to make this as ID matrix. The same operation you have to do here also. So this matrix will be your inverse of the matrix. So the A inverse is given by 3 by 2 minus 1 1 by 2, 1 by 2 0 minus 1 by 2, minus 3 by 2 1 1 by 2. This is the inverse of the matrix without using the formula, using elementary row operations. So the procedure is clear, right? You have to make A11 as 1 and make the corresponding columns as 0. That is first step. So make A11 as 1 and make A21 and A31. This is A21, A31. And similarly, you make after this here you make A22 as 1 and make A12 and A32 as 0 with the help of A22. After this, you have to make A33 as 1. See, the thing is, the idea is we are making this as 1 and make this as 0. We are making this as 1 and make this 2 as 0. We are making this as 1 and make these 2 as 0. First, you always have to make 1 and then you make the corresponding column 0 with the help of that 1. That is the idea. Is it clear? We'll move on to the next problem, right? Okay. So next question, a very simple question, carries 4 mark. So they have given A. We need to find A power 14 plus 3A minus 2y. There is no time to find A power 14 at all. So we will try to make use of Cayley-Hamilton theorem. So we will find characteristic polynomial for this. So what is the characteristic polynomial? Lambda q minus s1 lambda square plus s2 lambda minus s3. So what is s1? S1 is the trace of A. Trace of A is 1 plus 2 minus 3. So trace is 0. S2 is the sum of minus of principal diagonal, sum of minus of diagonals. So what this will be? So the minor for 1 is 2, 6, minus 1 and minus 3. And the minor for 2 is 1, 3, minus 2, minus 3. And the minor for minus 3 is 1, 1, 5, 2. So this will be what? Minus 6 plus 6. This is minus 3 plus 6. And this is 2 minus 5. So again this is 0, right? Minus 3 plus 3 will be 0. And S3 is the determinant of A. So determinant of 1, 1, 3, 5, 2, 6, minus 2, minus 1 and minus 3. This is 1 times minus 6 plus 6, minus 1 times minus 15 plus 12, plus 3 times minus 5 plus 4. So this will be 0. So you will have minus 3, this is plus 3, and then here we have minus 3. So determinant is also equal to 0. So the characteristic polynomial is given by lambda cube minus 0 lambda square plus 0 lambda minus 0. So we know every square matrix satisfies its own characteristic equation. Um, you know every square matrix satisfies its own characteristic equation by Cayley-Hamilton theorem. So that means A cube is equal to 0, right? You just replace lambda by A, you will be getting A cube is equal to 0. So we have A cube to be equal to 0. So that means we need to find A power 14, A power 14 plus 3A minus 2I. So A power A cube is 0 means A power 14 is also 0, right? Because A cube into A power 11 is A power 14. So that means A power 14 is also 0. So we will have 0 plus 3A minus 2I. So 3 times A. So A is 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3, minus 2 times I. So 2, 0, 0, 0, 2, 0, 0, 0, 2. So this will be, so 3 minus 2. So 3, 3, 9, 15, 6, 18, minus 6, minus 3 and minus 9, minus 2 times I. So subtract these two. So 13 minus 2 is 1. So 1, 3, 9, 15, 16 minus 2 is 4, 18, minus 6, minus 3, minus 9, minus 2 is minus 1. This is the value of A power 14, A power 14 plus 3A minus 2I, right? Okay. So 1, 3, 9, 15, 4, 18, minus 6, minus 3, minus 11 is our required value of A power 14 plus 3A minus 2I. So very simple problem. So we'll move on to the third one. Using elementary row operation, find the condition that the linear equation have a solution. So for what value of a, b, c, this will have a solution. So solution means it can be unique or it can be infinite also. That we will check by reducing to row echelon form. So this is um, find the condition on a comma b comma c. So actually they should give that this all, they should give that they should give the like some abcs are non-zero, right? If all abcs are 0, question is no use, right? Actually they should mention that some abcs are non-zero. Okay, no problem. So we will find the augmented matrix. So we will find the augmented matrix. So 1 minus 2 plus 1a, 2, 7, minus 3, B, 3, 5, minus 2, and C. Right? So we'll reduce this to row echelon form. So we have R2 is transformed to R2 minus 2 times R1. R3 is transformed to R3 minus 3 times R1. So this is equivalent to 1 minus 2 1a. So multiply 2 and then you subtract. You multiply 2, this will be minus 4. So 7 plus 4, this will be 11. You multiply 2, this is 2. So minus 3 minus 2, this is minus 5. This is b minus 2 times a. You multiply 3 and then you subtract. You multiply 3, this will be what? 2 3s are 6. So we'll have minus 6. Here we have 5. So 5 minus of minus 6. So 5 plus 6, which is 11. Minus 2 minus 3. So minus 5 again. R3 is C minus 3A. Right? C minus 3A. Now we'll make this as 0. So we have R3 is transformed to R3 minus R2. So this is equivalent to 1 minus 2 1a 0 11 minus 5 b minus 2a. So 0 minus 0 11 minus 0 minus 5 minus of minus 0. So here we have c minus 3a minus b plus 2a. Right, now we can see that. So we have see, surely it will not have unique solution, because you can see rank of A is 2, rank of A is 3, and rank of A comma B is 3 only will have unique solution. So surely this will have infinite or no solution. So this will have infinite solution. We have rank of A is equal to 2. For infinitely many solution, for infinitely many solution, uh, rank of A and rank of A comma B both should be equal to 2, right? So for rank of A comma B to be equal to 2, we should have this element to be equal to 0. If this element is 0 only, then you will have rank of A and the rank of A comma B both are equal to 2. So for this to be happen, we should have C minus 3A minus B plus 2A has to be equal to 0. That means C minus A minus B has to be 0, right? C minus A minus B has to be 0. So this is the condition on A comma B comma C for this to be have a solution. So that means C is equal to A plus B. So whenever C is equal to A plus B, have a solution, right? So it will have infinitely many solution. If C is equal to A plus B, it will not have unique solution, but it will have infinitely many solution if C is equal to A plus B. Is the condition on A comma B comma C. Okay. So we'll move on to the fourth problem. As of now, we have completed three problems. The first problem is based on finding the inverse of a matrix using elementary row operations. Second problem is using Cayley-Hamilton theorem. Third one is consistency based solution. So we'll move on to fourth problem. Actually, this is very over. They asked this for 3 mark. Actually, it is not worth it for 3 marks. They can ask for 10 marks also. But very this is not good. They asked only for this question for 3 mark. This has many idea in it. Okay, so we'll do this. So I'll tell you many ways and many insights for this problem. So here W1 consists of all those solution of this homogeneous system of linear equation, and W2 consists of all those solution of this homogeneous system of linear equations, and W3 consists of solution of this system of equations. Now first what we'll do is we will find individually, we will find the dimension for W1, dimension for W2, and dimension for W3. So W1 W1 is what? So W1 is x comma y comma z such that x plus y minus z is equal to 0. This is a homogeneous system of linear equations, right? So we have only one equation, but we have three free variables. So if I reduce this to row echelon form, we will have only one row. If I reduce this to row echelon form, you will have what? 1 1 minus 1 followed by 0 0 0 0 0 0 0 0 0. You just form dummy variables 0x plus 0y plus 0 z is equal to 0 like that. So you can see that the rank is 1, right? The rank is 1. Uh, rank is 1. So that means it will have how many free variables? So number of free variable is n minus rank of A. So we have two free variables, right? So let us assume y to be equal to k1 and z to be equal to k2. Then what about x? X is minus y plus z, right? So minus k1 plus k2. So therefore this solution set is given by x is minus k1 plus k2 and y is k1, z is k2. So that means you can see this solution set is spanned by minus 1 comma minus 1 comma minus 1 comma 1 comma 0 plus k2 times 1 comma 0 comma 1, right? So you can see there are two elements in the basis. And what about dimension? Dimension of w1. So dimension of w1 is 2. And what is the basis? One of the basis is what? Minus 1 comma 1 comma 0 and 1 comma 0 comma 1. So this is one of the basis. Now similarly we will find dimension for w2 as well as dimension for w3 also. So w2 here is w2 consists of all those x comma y comma z such that 3x plus y minus 2z is equal to 0. So again, when you reduce this to this homogeneous system of equations, you will have only one row that consists of 3, 1 minus 1 followed by all 0. So here also number of free variables. Number of free variable is total variable minus rank. Here also we have two free variable. So let us assume y to be equal to k1, z to be equal to k2. So we have 3x is equal to minus y plus 2z. So minus k1 plus 2 times k2. So that means x is given by minus 1 by 3 k1 plus 2 by 3 k2. So the solution space is given by, so x is minus 1 by 3 k1 plus 2 by 3 k2. I just check the questions once again, because if the question is wrong then everything will be wrong. So x plus y minus z is 0, 3x plus y minus 2z is equal to 0, x minus 7y plus 3z is equal to 0. Yes. So we have two free variables. So y is k1, z is k2. So our 3x is minus y plus 2z. So minus k1 plus 2 times k2. Yes. And then we have k1 comma k2. So that means k1 times minus 1 by 3 1 0 plus k2 times 2 by 3 0 1. So again you can see the basis has two elements and dimension of w2 is 2. See, some will simply say that dimension is nothing but total dimension of the vector space minus number of constraints. But I don't think that at all you can write in a subjective point of view. For shortcut point of view, if I simply say, I can say dimension is 2, right? But we will always do by this to impress the uh, whoever correctioning the paper. Okay, so we have dimension of w2 is equal to 2 and one of the basis is given by, you just multiply by 3 so that I don't, this will be looks good. You multiply by 3 throughout. So you will have to multiply by 3 minus 1 comma 3 comma 0. You multiply by 3 again, 2 comma 0 comma 3. So minus 1 comma 3 comma 0 and 2 comma 0 comma 3 is one of the basis. And similarly, that's why I said this category they asked this for 3 marks questions. But okay, so we have W3. See, if you want to use shortcut, you can directly write W2 to be equal to 2, but you should not write. So W3 consists of all those x comma y comma z, such that x minus 7y plus 3z is 0. So again, number of free variable. The number of free variable is total variable minus rank. So we have two free variable. So let us assume y to be equal to k1, z to be equal to k2. So x will be 7y minus 3z. So 7k1 minus 3 times k2. So our solution x comma y comma z is given by 7k1 minus 3k2 and then k1 comma k2. So k1 times 7 comma 1 comma 0, k2 times minus 3 comma 0 comma 1. So again dimension of w2 is again 2, w3. So dimension of w3 is 2 again, and one of the bases is given by 7 comma 1 comma 0 minus 3 comma 0 comma 1, right? Now actually we need to find dimension of w1 plus w2. So we know by dimension theorem, we know that so we know that dimension of, what do you need to find? Dimension of w1 plus w2. So dimension of w1 plus w2 is equal to dimension of w1 plus dimension of w2 minus dimension of w1 intersection w2. So dimension of w1 is what? Dimension of w1 is 2, w2 is again 2. So 2 plus 2 minus dimension of w1 intersection w2. So this is 4 minus dimension of w1 intersection w2. So we will find w1 intersection w2. So w1 intersection w2 consists of all those x comma y comma z such that x comma y comma z satisfies w1 as well as w2. So 3x plus y minus 3z is equal to 0. 3x plus y minus 2z is equal to 0. And then w3 x minus 7y plus 3z is equal to 0. Again you can see this is a homogeneous system of linear equations. So we have 3 1 minus 2 0, 1 minus 7 3 0, then we have 0 0 0 0, right? Just find the basis dimension for this. So we have r2 is transformed to 3 times r2 minus r1. So this will be equivalent to, oh okay, sorry, w1 intersection w2. I'm finding w2 and w3. I'm finding intersection. Just a minute. Dimension of w1 intersection w2. So w1 is x plus y minus z equal to 0. w2 is 3x plus y minus 2z is equal to 0. So just find the augmented matrix. 1 1 minus 1 0, 3 1 minus 2 0, 0 0 0 0. Reduce this. 1 1 minus 1 0. So multiply 3 and then you subtract. You multiply 3 and then you subtract. You multiply 3 and then you subtract. So minus 2 plus 3. Minus 2 plus 3. This will be 1 0 0 0 0 0. So number of free variable. Number of free variable is n minus rank of A. So rank is 2. So we have one free variable here. See, usually number of free variable will give you the dimension for homogeneous system when you are solving. So dimension is 1 for this. I don't think you need basis for this, right? Okay, let us find basis also. So we have x plus y minus z is equal to 0. Minus 2x plus y is equal to 0. So let us assume z is equal to k. We have minus 2y plus z is equal to 0. Just assume z is equal to k. Then what you will have? Minus 2y is equal to minus z. So y is equal to k by 2, and you can find x also, right? Dimension is 1. So dimension of, you will have only one element in the basis, that is k1 times of something. So w1 intersection w2 is 1, right? So you substitute here, 4 minus 1. So 3 is the dimension for w1 plus w2. Or you can also find dimension of w1 plus w2 in some other way also. I'll tell you all other possible way. Later. To find dimension of w1 plus w2, what you do is you write the you write the you write the basis elements you write the basis elements of w1, and you write the basis elements of w2. Now you find the rank for this matrix, that will be the dimension for w1 plus w2. So that is, what is the basis elements for w1? Basis elements of w1 is what? What are the base elements? Yes, minus 1, minus 1, 1, 0, minus 1, 1, 0, minus 1, 1, 0, and then we have 1, 0, 1. This is the base elements for W1. And right, base element of W2, W2 base element is minus 1, 3, 0, minus 1, 3, 0, 2, 0, 3. Now you find the rank for this, you will get the dimension for W1 plus W2. Like this, you will get the rank to be equal to 3 for this matrix. Uh, just find the rank for this to 3 for this matrix. Uh, just find the rank for this matrix. Minus 1, 1, 0. Add this. You subtract this. Hello everyone. So we'll continue. I think the internet issue. So I think the stream is stopped at here. I think, right. The stream is stopped somewhere around here. I'm telling the aliter to find the dimension of W1 plus W2. I'm telling the aliter to find dimension of W1 plus W2. What I'm saying is, you write the basis elements of W1 and W2. So what is the basis elements for W1? Base elements of W1 is given by minus 1, 1, 0, 1, 0, 1. That I'm writing here, minus 1, 1, 0, 1, 0, 1. And basis elements of W2. So basis elements of W2 is given by, that is given by minus 1, 3, 0, 2, 0, 3, minus 1, 3, 0, 2, 0, 3. You just find the rank for this matrix. You'll be getting dimension of W1 plus W2. I'm telling you an aliter, right? You can also find the same thing by finding the rank for dimension of W1. If you want to find dimension of W1 plus W2, you can also find the rank for this matrix. Rank is 3, right? So for this rank is 3. Dimension of W1 plus W2 is given by 3. This is an aliter. Now, that is why I said I don't understand why they are asking this question for 3 marks questions. Okay. Now we will find the dimension of W1 intersection W2 intersection W3. So we will find dimension of W1 intersection W2. This we have found now. It turns out to be 3, right? Turns out to be 3. Now we will find dimension of W1 intersection W2 intersection W3. So W1 intersection W2 intersection W3. So it consists of all those x comma y comma z such that our x comma y comma z should satisfy all three equations. X plus y minus z is 0, x plus y minus z is 0, and then 3x plus y minus 2z. 3x plus y minus 2z is equal to 0, and then x minus 7y plus 3z is equal to 0. So just have to find the dimension for this homogeneous, you have to find the dimension for the solution space of this homogeneous system. I think you can do this, right? We are solving many problems like this. So you just form the augmented matrix A comma O. You just form the augmented matrix A comma O. So we have 1 1 minus 1 0, 3 1 minus 2 0, 1 minus 7 3 0, right? 1 minus 7 3 0. So reduce this to echelon form. So R3 is transformed to R3 minus R1. R2 is transformed to R2 minus 3 times R1. So you will have this to be equal to 1 1 minus 1 0. You multiply 3 and then you subtract. You multiply 3 and then you subtract. You multiply 3, so you will have minus 3, minus 2 plus 3. Minus 2 plus 3 is 1, and it will be 0 again. So you multiply R1 minus R3 minus R1, so minus 7 minus 1 is minus 8. 3 minus half minus 1 is plus 4, and then this is 0, right? So this is equivalent to 1 1 minus 1 0, 0 minus 2 1 0. So you multiply 4 and then you subtract, this entire row will become 0, right? That is R3 is transformed to R3 minus 4 times R2. So you can see this is in row echelon form, and the number of free variable. So number of free variable is given by n minus rank of A. So n is 3, rank is 2. So we have one free variable, right? So we have one free variable. So let us assume z to be equal to k, and solve for x plus y minus z is equal to 0, and then we have minus 2y plus z is equal to 0, right? So this reduces to, let us assume um, let us assume y to be some k, right? Because it is easy for us to find other thing. So z will be 2k, then x will be what? Z minus y. So 2k minus k. Okay. So the solution space x comma y comma z is given by k comma z is 2k, y is k. So k comma 2k. So you can see it is spanned by 1 comma 1 comma 2, and there is only one linearly independent vector here. So therefore dimension is given by 1. So dimension of w1 intersection w2 intersection w3 is equal to 1. And suppose if they ask what is the basis for w1 intersection w2 intersection w2, one of the basis is given by 1 comma 1 comma 2, right? So very simple, it reduces to finding the solution of homogeneous system of equations, right? So dimension of w1 intersection w2 intersection w3 is 1, and dimension of w1 plus w2 is given by 3. Okay, so we completed 4 problems. So I think it is taking time to do all problems, very lengthy problems. So we'll move on to the next one. Okay, so first we have started with finding the inverse using elementary operations, and then we have found the Cayley-Hamilton theorem. We have found the power a power 14 plus 3a minus 2y, and then for what is the condition for this system to have a solution, and then they have given w1 w2 w3. They have asked about dimension of w1 plus w2 and dimension of w1 intersection w2 intersection w3 they have asked. So I will move on to the fifth problem. So there are 9 problems, so I'll go fast. So T is a map from M2 of R to P2 of R. So P2 of R is set of all polynomials of degree at most 2, right? I know everyone knows the basic. T consists of all those. T is a map from M2 of R to P2 of R. That map is given by, if you give a 2 by 2 matrix, it will take to P2 of R, that is given by A plus C plus A minus dx plus B plus C into x square. Find the matrix of T with respect to the standard basis of M2 of R and P2 of R. Also find the null space for this. So you can see T is a map from M2 of R to P2 of R. So P2 of R consists of all those polynomials of degree at most 2, right? At most 2. All 2-degree polynomials, all 1-degree polynomial and constant polynomials will be here. So what is the basis for M2 of R? What is the basis for standard basis for M2 of R? 1 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1, right? And what is the standard basis for P2 of R? Let us call this as B dash. It is 1 comma x square, right? With these two, with these three vectors, I can span P2 of R. Now, we need to find the matrix of T with respect to the basis. So we will find T of 1 comma 0 comma 0 comma 0. So you can see this maps to A plus C. So 1 plus 0 plus A minus D. 1 minus 0 into x plus B plus C. So B plus C is 0 x square. So this is equal to what? 1 plus x. Now we need to write this as a linear combination of basis vectors of codomain space. So we have to write this a linear combination of, let us say some, what we can do, let us say some c1 times 1 plus c2 times x plus c3 times x square. Obviously your c1 will be 1, c2 will be 1 again, c3 will be 0. I already said, right, if you want to find these coefficients, if it is a standard basis, then it is very easy to find those linear combinations, right? Okay, now similarly, so you can see your c1 c2 c3 will be my first column. So when this implies I can write it here itself, right? The value of c1 is 1, the value of c2 is 1 again, the value of c3 is 0. Now t of 0 1 0 0, so a plus c, so 0 plus 0 plus a minus d, a minus d is 0 again into x plus b plus c, so b plus c is 1 into x square, right? Okay, so this is nothing but x square. Now we have to write this x square as a linear combination of basis vectors of codomain space. Let us say some c4 times 1 plus c5 times x plus c6 times x square. So very easy to find these coefficients. The c4 has to be 0, c5 has to be 0, c6 has to be 1. Now we will find the third one. So t of 0 comma 0 comma 1 comma 0. So a plus c. So a plus c is 1. A minus d. So a minus d is 0 into x plus b plus c. So b plus c is 1 x square. So we have 1 plus x square. So write this as a linear combination of basis vectors of P3. So that is some C7 times 1 plus C8 times x plus C9 times x square. So your C7, C8, C9 will be equal to 1, 0 and then 1 again. And the last basis vector of domain space T of 0 comma 0 comma 0 0 0 1. So T of 0 0 0 1 a plus c. So a plus c is 0, a minus d. So a minus d is minus 1 into x, and then we have b plus c is 0 again, which is equal to minus x. So write this as a linear combination of basis vector. Let us say some c10 times 1 plus c11 times x, c12 times x square. So this reduces to, what is our c10? 0, minus 1 and 0. So therefore the matrix of T with respect to the standard basis of M2 of R and P2 of R is given by 1 1 0 1 1 0 0 0 1, right, 0 0 1 1 0 1 1 0 1 and then 0 minus 1 0. This is a matrix of T from M2 of R to P2 of R that is given by standard basis, right? Okay. Yes, can I move on to the next one? Now the next thing is after finding the matrix of T, we need to find the null space also. Okay. So we'll find null space of T also. So we will find null space of T. So null space of T consists of uh, all those matrix. What is null space? All those elements in domain space that is mapping to zero vector of codomain space, right? So that we will find. So we need to find all those matrix that is mapping to zero vector of P2 of R. Um, so I'm finding all those x in M2 of R such that T of x is equal to 0. This 0 is a zero vector of polynomials, that is 0x 0 plus 0x plus 0x square, right? Okay. um okay, so that means we have to find all those x such that T of x is 0. X is a element of M2 of R, right? So we will find all those x such that T of x is 0. So let us take x to be or else we can do like some other thing also. So okay, uh, so T of, let us take x to be some a b c d, right? Because x is M2 of R is equal to 0. Now, what is T of A, B, C, D? We know the map, right? A plus C. This is a zero vector of P2 of R, which is 0x, 0 plus 0x plus 0x square. So, A plus C plus A minus D into x plus A minus D into x plus B plus C into x square is equal to 0 plus 0x plus 0x square. Now, we can see A plus C is 0, A minus D is 0, and then we have B plus C is equal to 0. That means A is equal to minus C, A is same as B, B is equal to minus C. I can write the basis directly, right? So our x is given by A, B, C, D, and we know if it is mapping to 0, A is of the form minus C, B is of the form minus C. Let us keep C as it is. B is A and A is minus C, right? That means if I take C outside, you can see this is the basis for null space of T, right? Null space of T is spanned by basis for null space is given by the matrix minus 1 minus 1 1 minus 1, right? Because all those ABCD is of this form, because we are getting this matrix by solving equating to zero vector of P3, right? So this is the basis for null space, and you can see all those matrix of this form. When you multiply C with any, you multiply this matrix to any scalar, all this matrix will map to zero vector of P2 of R. You can check it out, right? You just take this matrix minus 1 minus 1 1 minus 1. What is the operator? A plus C. What is A plus C? A B C D. A plus C is 0. A minus D. A minus D again 0. B plus C. B, C is 0. So you can still map to 0 vector of P2 of R. So basis for null space is given by minus 1 minus 1 1 minus 1, and the dimension is what? Dimension of null space is 1. What they have asked actually, uh, further find null space of T. So null space of T consists of all those, all these kinds of matrix, right? We use the null space of T. All those matrix of this form will be in null space of T because all those elements, all those matrix of the form will map to zero vector of P2 of R. Is it clear? Is it clear till now? So fifth problem, 10 mark question. So M2 to P2. Now we need to write the output vector as a linear combination of basis vector of codomain space. Standard basis is the basis for codomain space they have given. Now find these coefficients scalars C1, C2, C3. That will be my columns for corresponding matrix of T. Right? Okay. We move on to sixth problem. T is a map from P2 of x to P3 of x. So P2 is a polynomial of degree less than or equal to 2, and that is at most 2, and P3 is a polynomial of degree at most 3. All those polynomials of degree at most 3, at most 2. So it maps P2 to P3 given by the operator P of f of x is equal to f of x plus 5 times integration of 0 to x f of t dt. Then choosing this as a basis for P2, this as a basis for P3, find the matrix of T. Very simple question. So, T is a map from P2 to P3. So set of all polynomials of degree at most 2, set of all polynomials of degree at most 3. So this basis is given by, 1 comma 1 plus x comma 1 minus x square, and this basis is given by, let us call this b dash 1 comma x square comma x cube, right? So we will find t of 1 plus x, t of 1 minus x square. We will do this. So first we will find t of 1. So our f of x is 1. So f of x, so our f of x is 1. So 1 plus 5 times integration of 0 to x f of t dt. So 1 times dt. So this will be what? 1 plus 5x. Yes or no? Integration of dt is t, upper limit minus lower limit. Now you have to express this as a linear combination of our codomain space. For codomain space, basis is this. So write this as linear combination of basis vector c1 times 1, c2 times x, c3 times x square, c4 times x cube. So obviously you can find c1, c2, c3, c4 directly. And similarly, you find a t of 1 plus x. So your f of x is 1 plus x. So f of x plus 5 times integration of 0 to x f of t dt. So f of t is 1 plus t dt. Sir, no. F of x is 1 plus x. So f of t is 1 plus t. So this will be 1 plus x plus 5 times. So integration of 1 plus t dt. So integration of dt is t. Integration of t dt is t square by 2, 0 to x. This is 1 plus x plus 5x plus 5x square by 2, upper limit minus lower limit. So x plus x square by 2. So we will have 1 plus 6x plus 5x square by 2. Now you have to write that as a linear combination of, let us say, some c5 times 1, c6 times x, c7 times x square plus c8 times x cube. Okay. Now we will find t of 1 minus x square. So f of x is 1 minus x square. So f of x, so 1 minus x square plus 5 times integration of 0 to x 1 minus t square dt. So this will be 1 minus x square. Integration of t dt is t. So you will have 5x and then t cube by 3. So that means you will have minus 5x cube by 3. Now you have to write this linear combination of basis vectors of codomain space C9 times 1, C10 times x, C11 times x square plus C12 times x cube. Now find C1, C2, C3, C4. So obviously your C1 is 1, C2 is 5, C3, C4s are 0. Here your C5 is 1, C6 is 6, C7 is 5 by 2, and this is 0. And what is your C9? C9 is 1, C10 is 5, C11 is minus 1, and C12 is minus 5 by 3. So therefore, the matrix of T with respect to the given basis is given by 1500, 1500, and then 165 by 20, 165 by 20, 15, 15, 15, minus 1 minus 5 by 3. This is the matrix of T with respect to the given basis and with respect to the given operator. Okay. So we'll move on to next one. So this carries 6 marks, right? So only thing is you have to input this vector, write the output as a linear combination of basis vector of codomain space. Those linear combinations, you call that will be the corresponding columns for each matrix, right? Okay. So still there are 3 problems. We'll do that. So if A is equal to 110, 110, 001, find the eigenvalues and eigenvectors of A. So very standard problem. So they are given a matrix. For that matrix, you need to find the eigenvalues and eigenvector. Actually, again, this is a lengthy problem. I don't know why they are asking this lengthy problems at all. For 8 marks, now the question number is okay, right? 24, 23, 22 at all. But this previous years at all, that 15, 16, 14 at all, very lengthy paper, each paper. Okay. So the matrix A given, find the eigenvalues and eigenvectors of A. So I hope everyone knows how to find that, because the previous classes itself we know how to find. The previous videos itself I have explained how to find eigenvalues and eigenvectors of A, right? So I'll find eigenvector for something and then I'll leave an exercise for you. So first I'll find eigenvalues. Eigenvalues are the roots of characteristic polynomial. The characteristic polynomial is given by lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0, right? So what is s1? S1 is trace. So we will have lambda cube minus trace is 3, 3 lambda square. Now uh, what is s1? S1 is trace, which is equal to 3. Now what is s2? Is the minor of principal minus. So one minor is 1001, and then a minor for this one is 1001, and then the minor for this is 1111. So this is 2, right? And S3 is determinant of A. So determinant of 110, 110, 001, it will be 0 because two rows are identical. So this is given by lambda cube minus 3 lambda square plus 2 lambda minus 3 is equal to 0. That means just take lambda outside. So lambda square minus 3 lambda plus 2 is equal to 0. So that means lambda is equal to 0, or lambda square minus 3 lambda plus 2 is equal to 0. What is the root? Solve for this, right? Uh, 2, 3, 2. I think 1 and 2 are the roots, right? So here lambda is equal to 1 and 2. So therefore the eigenvalues are given by the eigenvalues are 0, comma 1, comma 2, right? 0, comma 1, comma 2 is the eigenvalues. Now we'll find eigenvector. Now we'll find eigenvector for each eigenvalues, right? Okay. So I'll find eigenvector corresponding to 1. Uh, from other onwards you can find, right? You know, if you have watched all my previous videos, you know how to find the eigenvectors. So eigenvector corresponding corresponding to lambda is equal to 1, I'll find first. A non-zero vector x is called eigenvector if ax is equal to lambda x. So we have a minus lambda I of x is equal to 0. This x is our eigenvector. So find x. So lambda is 1 first. So 1, 1, 0, 1, 1, 0, 0, 0, 1 minus lambda I 1, 0, 0, 0, 1, 0, 0, 0, 1. So 1 minus 1 is 0, 0, 1, 0, 1, 1 minus 1 is 0, 0, 0, 0, 0 times, let us say x1, x2, x3 is an eigenvector equal to 0, 0, 0, right? Now solve for x1, x2, x3. Now you can see this rank is 2 for this. We reduce to augmented matrix. If you form an augmented matrix, you just have to solve this homogeneous system of linear equations. So here rank will be equal to 2. So in that case, your number of free variable will be equal to 1. So let us assume what? Z x3 to be equal to k. Now if you solve this equation, you will have x2 is equal to 0, x1 is also equal to 0, right? X2 is 0, x1 is 0, and x3 is k. So the eigenvector corresponding to this eigenvalue lambda is given by 0, comma 0, comma k. We take k outside. 0, comma 0, comma 1 is the basis vector for the eigenspace corresponding to lambda is equal to 1, right? Okay. Is it clear? So our A matrix is, I'll just check the question once again. Our A matrix is 1 1 0 1 1 0 0 0 1. So we just check this. We just check this. Tuani, is it correct? Eigenvector corresponding to lambda is equal to 1. So I'm putting lambda to be equal to 1. Then A minus lambda x is equal to 0. So 1 minus 1 is 0. And then we will have 1 0 1 0 0 and 0 0 0. So rank is 2. So we have one free variable. So I'm assuming x3 to be k. Then we have x1 and x2 are 0. Yes. So 0 comma 0 comma 1 is the basis for the eigenvectors corresponding to lambda is equal to 1. Basis for eigenspace for lambda is equal to 1 and dimension is 1 also. Okay. So eigenvector corresponding to lambda is equal to 2 again. So eigenvector corresponding to lambda is equal to 2. So we have A minus lambda I x is equal to 0. So what is the matrix A? 1 1 0 1 1 0 1 1 0 1 1 0 0 0 1 minus lambda I 2 0 0 0 2 0 0 0 2 x is equal to 0. So 1 minus 2 is minus 1 1 0 1, 1 minus 2 is minus 1, 0. Then we have 0, 0, minus 1, x1, x2, x3 is equal to 0, 0, 0. Now, when you form an augmented matrix A, comma O, this is equivalent to minus 1, 1, 0, 0. Let us shift this rows 0, 0, minus 1, 0, and then you add these two. You're getting this is 0, 0, 0. Again, you can see rank is rank of A is 2. So number of free variable. So number of free variable is n minus rank of A. So we have one free variable. Let us assume x3 to be k. So when equation will have minus x1 plus x2 is equal to 0, and then we have minus x3 is equal to 0. Let us assume x2 to be equal to k. Right? So this means our x1 is also k and our x3 is 0. So the eigenvector eigenspace is given by what is x1? x1 is k, x2 is k, x3 is k. So k times 1 comma 1 comma 0 is the eigenvector corresponding to lambda is equal to 2, right? So 1 comma 1 comma 1 comma 0, right? Okay. So 1 comma 1 comma 0 is the eigenvector corresponding to lambda is equal to 2. And similarly, we will find eigenvector corresponding to lambda is equal to 0. So a minus lambda x is equal to 0. A minus lambda x is equal to 0. So lambda is 0. So a minus x, it turns out to be 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1 times x1, x2, x3 is equal to 0, 0, 0. So if I reduce this augmented matrix, this will be like 1, 1, 0. You shift the rows 0, 0, 1, and then you subtract 0, 0, 0. Yes or no? Just form the augmented matrix. I'm just reducing the augmented matrix to echelon form. And again, you can see number of free variables is equal to total number of variables minus rank. So rank is 2. So we have one free variable. And what are the equations we have? x1 plus x2 is equal to 0. x3 is equal to 0. So let us assume x2 to be equal to k. Then x1 will be minus k. So the eigenvector corresponding to 0 is given by minus k, k, 0. So if we take k outside, minus 1 comma 1 comma 0 is the basis for eigenspace corresponding to lambda is equal to 0, right? So that's it. We have completed this problem. Find the eigenvalues and eigenvectors of A. The eigenvalues are 0, 1, 2. Eigenvector corresponding to 0 is given by minus 1, 1, 0, one of the eigenvector. And the eigenvector corresponding to the eigenvalue 1 is given by 0, 0, 1. And eigenvector corresponding to 2 is given by 1, 1, 0. Right? Okay. Okay. So move on to eighth problem. Just a minute. I'll have some water and come. Okay, so I will move on to eighth problem. Prove that the eigenvectors of an Hermitian matrix are eigenvalues of an Hermitian matrix are real. So we know what is meant by Hermitian matrix, right? So when we call a matrix A to be Hermitian matrix, so A is an Hermitian matrix, Hermitian or Hermatian. So A is an Hermitian matrix if A is equal to A star. What is A star? A is equal to A bar transpose. So here the entries can also be complex number. So if your all the entries are real number, then your A bar is same as A, then it will reduce to symmetric matrix. If the entries are complex number and if A is equal to A bar transpose, then we say how to find A bar? You just find the bar for each entries. For example, if you have a matrix A to be, let us say I 1 plus 2i 1 and 2. Now what is A bar? A bar is given by conjugate for each element. 1 minus 2i conjugate for real number is same only, right? Now what is A bar transpose? What is A bar transpose? Minus I 1, 1 minus 2i 2. Now you can see this A and A bar transpose are not equal. That means this matrix is not Hermitian matrix. Suppose if A is equal to A bar transpose, then we say that the matrix is this is not Hermitian matrix because A is not equal to A bar transpose, right? So this is not Hermitian matrix. Suppose if all the entries are real number, what's the bar for real number? It is same only, right? Z bar is same as Z if Z is real number, complex numbers basics. So this is not an Hermitian matrix. Suppose you put bar for each entries, that is you put conjugate for each entries, and then you transpose the matrix, you have to get the back A matrix again. If that happens, we say that the matrix A is an Hermitian matrix. That A bar transpose I'm writing as A star just for simplicity. Okay, now we need to prove that the eigenvalues are of an Hermitian matrix are always real, right? That is, if I want to show some number is real number, how do I need to prove? What I need to prove? Uh, Let us say some x is real, a number is real number if conjugate is same as that number. That is, you put conjugate. What is the conjugate for real number? It is same, right? What is the conjugate for 3? 3 can be written as 3 plus 0i. Conjugate is 3 minus 0i. Both are same only. So let lambda be the eigenvalue of A. To prove what? To prove this lambda is real, right? This lambda is real. So for that, what I need to prove? To prove lambda is real, that is, I need to prove lambda is same as lambda bar. Conjugate is same as that number. That means you will get that number to be a real number, right? Okay. So let lambda be the given. What is given? Given A is a Hermitian matrix. Given A is a Hermitian matrix. That means A is same as A star. What is A star? A star is A bar transpose. Okay. So let lambda be the eigenvalue. Let lambda be the eigenvalue of A and x be the corresponding eigenvector and x be the corresponding eigenvector, right? X be the corresponding eigenvector. Then we have by definition Ax equal to lambda x. Is it clear up to now? So what I need to prove? I need to prove this number lambda is a real number, right? Okay. So what I'll do is I'll pre-multiply by x star. I'll pre-multiply by x star. I'll pre-multiply by x star. So we have x star Ax is equal to x star lambda x. Is it clear? I'm pre-multiplying by lambda star. See, whenever I put star, that is nothing but what? Bar transpose. Okay. Now I'm taking star on both sides. I'm taking power star on both sides. So x star ax whole star is equal to x star lambda x whole star. Is this clear? So I'm just first I'm pre-multiplying by x star, and then I'm taking star on both side, and then I'm taking star on both side. So just say star, you can always compare the star with the properties of transpose, right? So A B transpose, B transpose, A transpose. So you will have this to be this. You will have this to be equal to, you apply star in the reverse direction. So x star A star x star A star. Then we have x star star is equal to, and then you apply in the reverse direction, x star lambda star x star star. You can always visualize star properties in transpose. A transpose transpose is A. So we have x star A star x, and here we have x star lambda star x. Right? Now A star is same as A, we know, right? Because this A is a Hermitian matrix. So x star Ax. What is lambda star actually? What is lambda star? Lambda is nothing but lambda bar. Yes or no? Lambda, what is A star? A bar transpose. This lambda is scalar. There is a number. Number, you are putting conjugate and then you are transposing a number. That is same, right? If you are transposing a single number, it is same only. 1 cross 1 matrix, right? A number. So you will get lambda star to be lambda bar. Now, x star, can I write Ax as lambda x? Let us call this as 1, call this as 2. This is by 1. By 1, A star is equal to A. So I'm writing this A star to be A, and then I'm using Ax to be lambda x by 2. X star lambda bar x. Right? Now, uh, also note that lambda star is this lambda bar, right? Lambda bar is lambda bar transpose. Lambda is a scalar, single scalar. So transpose nullify. It will not affect the system. Okay. Now this can be done as, if I take x star common, so lambda minus lambda bar of x is equal to 0. See, this x is an eigenvector. So eigenvector is always a non-zero vector. So that means this will never be 0. This will never be 0. So this implies lambda minus lambda bar has to be 0. So you will have lambda is equal to lambda bar. This implies lambda is a real. So we have proved. Very simple proof. We need to prove that the eigenvalues of an Hermitian matrix are real number. So you start with this, right? You start with this. You pre-multiply by x star, and then you take star on both sides. Use the properties, and then you prove that lambda is equal to lambda bar. Clear? We'll move on to the next problem and final problem. Is it clear up to now? Is it clear up to now? We'll move on to the ninth one and the last one. Okay. So last problem, lengthy problem, as well as tricky problem, as well as very very good problem. This carries 18 marks, right? So with this, we'll wind off this paper. Let A is a matrix given by A is a matrix. I try to complete this in 15 minutes. So time is 1:56 now. Okay. A is a matrix given by 1 minus 1 2 minus 2 1 minus 1 1 2 3 is a matrix of linear transformation if T is a matrix of linear transformation if T is a map from P2 to P2 with respect to the basis this, then find D. Okay. See, we need to find the matrix, we need to find the corresponding transformation, right? Such that they have given the matrix of T with respect to this basis, right? So what they have given is they have given a matrix of T with respect to the basis. See, here T is a map from P2 of x to P2 of x, right? T is a map from P2 of x to P2 of x. So for this domain space, the basis is given by, for this domain space, the basis is given by 1 minus x, x into 1 minus x, x into 1 plus x, right? And for this codomain space, the basis is given by 1 comma 1 plus x comma 1 plus x square, right? Now the matrix of T with respect to this basis is given by this, right? The matrix of T, right? The matrix of T with respect to the basis of domain and codomain space for with respect to this basis is given by the matrix 1 minus 1 2 minus 2 1 minus 1 1 2 1 3. Now we need to find generally the explicitly we need to find the map. We did some problems, right? They will give a map from R2 to R2. T of 1 comma 2 is 3 comma 4. T of 5 comma 6 is some 10 comma 4. Find T of x comma y, like that problem. But in those problem at all, the basis is standard basis for both domain and codomain space. It is very easy. But here basis is not standard basis for domain space as well as codomain space, right? Both are P2 only, but they are giving you two different bases for domain space and codomain space, and this is the matrix of T with respect to this transformation, right? Now we need to find explicitly, you give any, that is you need to find a map T, that T a plus bx plus cx square, you need to find a map, right? Because P2 to P2, right? You give any polynomial in P2, you tell me a map such that that maps takes this basis vector to this matrix, and also explicitly you find a map, right? You find a map which takes 1 minus x to 1, x into 1 minus x. No, what they are asking is, yeah, no, I haven't asked like that. Okay, you need to find the matrix, we need to find the linear map in general, right? You need to find the linear map in general so that this 1 minus x has some output vector. That output vector, you need to write that as a linear combination of basis vector of codomain space. That linear combination is given by this matrix. I'll explain, right? Don't worry. So we will find a general map, right? We will find a general map. So we'll pass this question here. As of now, what we'll do is, uh, as of now, what we'll do is, um, P is a map from 1 minus x, x into 1 minus x, x into 1 plus x. Okay. So we'll do this problem now. So as of now, what we'll do is we'll find the linear map. First, what we'll do is we will see where this P of 1 minus x maps. Right. Now, T of 1 minus x. What is T of 1 minus x? It will be some output vector that we don't know. It will be some vector we don't know. But we can always write this vector as a linear combination of basis vectors of codomain space. Yes or no? Yes. So that means we can always write this as a linear combination of basis vectors of codomain space. That codomain space basis vector is 1, 1 plus x, 1 plus x square. 1, 1 plus x, 1 plus x square. Now we don't need to find C1, C2, C3. We know C1, C2, C3, C3. They are given the matrix, right? So that means this turns out to be your C1, C2, C3. Yes or no? You just think of it. How usually you will find the corresponding. You will find the first column of the matrix with respect to some bounded basis, you will write the output vector as a linear combination of basis vectors of codomain space. That linear combination elements will be your code first column. So that means your C1, C2, C3 has to be equal to what? 1 minus 2, 1, 1 minus 2 and 1. 1 minus 2 and 1. Yes or no? So that means your T of 1 minus x has to be equal to what? 1 minus 2 into 1 plus x plus 1 into 1 plus x square. So 1 minus 2x plus x square. So 1 plus 1 minus, so minus 2x plus x square is the output for 1 minus x. Is this step is clear? So T of 1 minus x is minus 2x plus x square. Is this clear? Now similarly, we will find output for second uh, vector, the basis of domain space, x into 1 minus x. X into 1 minus x. Now we don't know what this is, but it can be written as a linear combination of C4 times 1 plus C5 times 1 plus x plus C6 times 1 plus x square. So your C4, C5, C6 is turns out to be what? So your C4, C5, C6 is minus 1, 1, 2. Minus 1, 1, 2. Yes or no? This is how usually you know this. You will find C4, C5, C6 by equating. But we are doing vice versa. You know these coefficients already because you know the matrix of T. Okay, so that means this will be equal to minus 1 plus 1 plus x plus 2 plus 2x square. So minus 1 plus 1. So 2 plus x plus 2x square. Is it clear up to now? 2 plus x plus 2x square is the output for x into 1 minus x. Now we will see where the next vector maps to. The next vector is what? X into 1 plus x. So we don't know what this is. But this can be done as a linear combination of C7 times 1, C8 times 1 plus x, C9 times 1 plus x square. And we know the third column in our matrix of T is 2 minus 1, 3. So this has to be 2, this has to be minus 1, this has to be 3. So you have this to be equal to 2 minus 1 minus x plus 3 plus 3x square. So 2 minus 1 is 1, 1 plus 3 is 4. So 4 minus x plus 3x square. So 4 minus x plus 3x square is the output for x into 1 plus x. Is it clear up to now? Is it clear? See, still very core part left in the problem. As of now, what we did is we have found where t of 1 minus x maps, where t of x into 1 minus x maps, and where t of x into 1 plus x maps. This reduces to the one that you already know, right? If you know them, if for example, there are some problems that we have solved, like there are some problems we have solved like t of 1 comma 2 is 1 comma 3, t of 2 comma 5 is some 3 comma 10. We know how to find t of x comma y, right? How you will find x comma y? You take an x comma y in R2. That x comma y is written as a linear combination basis vector. Now you have to find that x comma y in terms of that is you take any x comma y in R2. Then x comma written as some a into 1 comma 2 plus b times 2 comma 5. We will solve for a b in terms of x y. Apply t on both sides. You will get t of x comma y. Yes or no? These kinds of problem already we did many kinds of problem. This reduces to same kind of problem, right? This reduces to same kind of problem, but the thing here is the basis is different for domain space and codomain space, right? You just compare the same problem with this problem. Here we have T is a map from P2 of x to P2 of x, right? T is a map from P2 of x to P2 of x, and this basis is given by what? 1 minus x. This basis is given by 1 minus x, x into 1 minus x, x into 1 plus x, and this basis b dash is given by 1 comma 1 plus x comma 1 plus x square, and we know this t of 1 minus x maps to minus 2x plus x square. T of x into 1 minus x maps to 2 plus x plus 2x square, and T of x into 1 plus x maps to 4 minus x plus 3x square. In general, you find me where T of a plus bx plus cx square maps. Is the question is now clear? Is the question is now clear? Right? This is now the question is. We know this maps to this, this maps to this, maps to this. In general, you take any vector in P2 of x, any vector in P2 of x is of the form ax plus a plus bx plus cx square. You see where it maps to. Is it clear? Now we will find that map, right? Now this is how we need to find it. Let us take a vector. Let us take a plus bx plus cx square in P2. That is your domain space. That is your domain, right? Domain space. Now this can be written as any vector in the domain space can be written as a linear combination of basis vectors of domain space. Yes or no? Let us say that scalars are some alpha 1 times. What is the basis vector for domain space? 1 minus x, 1 minus x, some okay, let us write alpha, beta, gamma. X minus x square. Yes or no? I'm taking an arbitrary vector in the domain space, which is a plus bx plus cx square. That vector can be written as a linear combination of basis vectors of domain space. Basis vector of domain space is 1 minus x, x into 1 minus x, this x into 1 minus x, this is x into 1 plus x. Right. Now solve for alpha, beta, gamma, like same as that kind of problem. Solve for alpha, beta, gamma in terms of this ABC. Okay. Now what you will have? A plus bx plus cx square is equal to alpha. You just collect all those x coefficients minus alpha plus beta plus gamma x. You collect all x square coefficient minus beta plus gamma. Yes or no? So that means the value of alpha is a minus alpha plus beta plus gamma is b minus beta plus gamma is given to be c. Now solve for alpha, beta, gamma in terms of ABC. Solve for alpha, beta, gamma in terms of ABC. See, if you have watched all those previous videos, the one which I am trying to say will be very easy for you. I give an example, right? T of 22, 4 maps to this. T of 3, 10 maps to this. Where T of x, y maps. That is the same thing here also we are doing, right? Now solve for alpha, beta, gamma. Now you add these two equations, right? You add these two equations, you will have minus alpha plus 2 gamma is equal to b plus c. That means 2 gamma is equal to alpha is a, right? So a plus b plus c. So the gamma value is a plus b plus c by 2, right? Alpha is a, gamma is a plus b plus c by 2. and we know beta is here. From here we can find beta, right? Beta is equal to gamma minus c. So gamma is a plus b plus c by 2 minus c. So your b a plus b minus c by 2 is the value of beta. So that means this a comma this ax, that is any vector in the domain space, any vector in the domain space a plus bx plus cx square can be written as a linear combination of alpha times, can be written as linear combination of basis vectors of domain space. So basis vector of domain space is alpha into 1 minus x plus beta into x into 1 minus x plus gamma into x into 1 plus x. We have found alpha, beta, gamma. We'll substitute later. Now we apply t on both sides. Same thing that we did there, we are doing here also, right? Don't think it is different. Now apply t on both sides. So t of a plus bx plus cx square is equal to alpha into t of 1 minus x plus beta into t of x into 1 minus x plus gamma into t of x into 1 plus x. We know the value of t of 1 minus x. We know the value of t of x into 1 minus x. We know the value of t of x into 1 plus x. That is why we have found all these values. T of 1 minus x, t of x into 1 minus x, t of x into 1 plus x. Right? Okay. We'll substitute here. Is equal to what is alpha? Alpha is a. What is t of 1 minus x? What is t of 1 minus x? Minus 2x plus x square minus 2x plus x square plus beta. So beta is a plus b minus c by 2. What is t of x into 1 minus x? T of x into 1 minus x is 2 plus 2x square. 2 plus 2x square plus what is gamma? Gamma is a plus b plus c by 2 times what is t of x into 1 plus x. T of x into 1 plus x is 4 minus x, 4 minus x plus 3x square. That's it. We are going to find the map. Now you collect all the x coefficients, all the constant term, all the constant term. Here there is no constant term. Here the constant term will be what? You multiply 2 with this. So 2 will get cancelled. A plus b minus c. Here the constant term is, here the constant term is 2a plus 2b, 2a plus 2b plus 2c, right? 2a plus 2b plus 2c. Yes or no? See, I'm just collecting all the constant term. This is constant term, this is constant term. Here 2 will get cancelled. Now you collect all the x terms. Here you will have minus 2a, right? Here you will have uh, plus. You collect all the x terms now. You collect all the x terms. What you will have? Minus 2a. Here the x term is a by 2 plus b by 2 minus c by 2, and here the x term is minus a by 2 minus b by 2 minus c by 2. Or no? I'm just collecting all the x terms, that's it. Like terms minus 2a. Here the x term, x coefficient is a plus b minus c all divided by 2. Here the x coefficient is minus a by 2 minus b by 2 minus c by 2. You collect all the x square term. You collect all the x square term. Here you will have a. Here you will have what? 2 will get cancelled. So a plus b minus c. Here the x square term is what? Here the x square term is 3 by 2 of, so that means 3a by 2 plus 3b by 2 plus 3c by 2. Yes or no? I'm just collecting all the x terms, x square terms, T of x into 1 minus x value. Raghavi, this one. T of x into 1 minus x value. So T of x into 1 minus x, 1 into 1 plus x, 1 plus x square. So we know the matrix is minus 1, 1, 2, minus 1, 1, 2. So minus 1 plus 1 plus x plus 2 plus 2x square. So 2 plus x plus 2x square. That only I think, right? 2 plus x plus 2x square. That only I think. Or else we will see whether we are getting the answer or not. If else we will check. Okay. We have got our map T. So T of a plus bx plus cx square is equal to what is our constant term? Constant term is 3a plus 3b minus c. 3a plus 3b minus c plus what is our x term? These two will get cancelled. These two will get cancelled. So minus c by 2 minus c by 2 is minus c. So we have minus 2a minus c times x, right? Minus 2a minus c times x. Now you collect all the x square term. A plus a plus a is 2a, 2a plus 3a by 2. 2a plus 3a by 2 is 7a by 2. B plus 3b by 2. So 2b plus 3b. So 5b by 2. And then you collect all the c terms. Minus 2c plus c by 2. This is the linear map. This is the linear map, right? This is the linear map. Quite lengthy problem, but very good problem. Can we check whether it is correct or not? Can we check whether it is correct or not? Can we find where T of 1 minus x maps? Can we find where for this map? Can we find where T of 1 minus x maps? So for 1 minus x, what is our A? A is 1, B is minus 1, C is 0. We are finding generally for any A plus Bx plus Cx, this is the map. Can we check whether our T is correct or not? You just find a linear map where T of 1 minus x maps. So T of 1 minus x maps. A is 1, B is minus 1, C is 0. Substitute here 3 into 1, 3 into A plus 3 into B. So 3 into 1 plus 3 into minus 1. This will be 0 plus x times minus 2a minus c. So minus 2a is, so this will be minus 2, right? Plus x square term, 7a by 2 is 7 by 2. 5b by 2 is minus 5 by 2. And c by 2 is 0. Simply getting what? 0 minus 2x. 2 by 2 is 1. So minus 2x plus x square. Yes, minus 2x plus x square. Our map is correct. Our map is correct. This is a general map that takes any vector of P2 to P2 with that with respect to this spaces, and that matrix is given by this matrix, right? We can also check for this also, right? We will check one more also. So we will find where T of x minus x square maps. T of x minus x square. T of x minus x square. We will see where this maps. T of x minus x square. T of x minus x square. We will see where this maps. T of x minus x square. A is 0, B is 1, C is minus 1. A is 0, B is 1, C is minus 1. So 3 into 1 You will be getting constant term as 4 plus x times minus 2a, this is 0, minus c will be plus 1 plus x square term 7a by 2, it will be 0, 5b by 2 is 5 by 2 plus c by 2 will be minus 1 by 2. So 4 plus x, this is 4 by 2 is 2. 4 plus x plus 2x square. 4 plus x plus 2x square. We are getting 2 here. We are getting here what? A is 0, B is 1, C is minus 1. That is why you said to check this 4. Oh. Minus 1, 1, 2. Minus 1, 1, 2. We should get 2 plus x plus 2x square, right? We are getting 2 plus x plus 2x. We should get, we are getting 4 here, but should get 2. Is there any mistake I have made? Is there any mistake I have made? Minus 2a minus c. This is 3a plus 3b minus c, minus c or plus c. We'll check this. I'll check this alone. Uh, okay. It is plus c, right? 2a plus 2a is 3a. B plus 2b is 3b. 2c minus c is, this is plus c. Yes, this is plus c. Yes, now we'll be getting the answer. Correct only. This is plus c. So in that case, you will be getting B is 1, C is minus 1. So you'll be getting 2. So 2 plus x plus 2x square, right? You can check in the first case also. If you take 1 minus x, if you take 1 minus x, A is 1, B is minus 1. So A is 1, B is minus 1. Yes, correct only. So this is, here we're getting plus. So it's a required linear map. So we need to find a map explicitly where we are finding explicitly the map, right? So this is the linear map. Is the required linear map. Is the required linear map, right? So I'll explain once again. Tricky problem, but it is very simple only. You just have to understand the concept. So what we did is we know the matrix of T that takes this basis that with respect to these two bases. We know the matrix of T. That means this T of 1 minus x we don't know, but that T of 1 minus x can be written as a linear combination of basis vector of codomain space. So T of 1 minus x can be written as a linear combination of basis vector of codomain space. We don't know C1, C2, C3, but we know the matrix of T with respect to the basis. We know what is the matrix of T with respect to the basis. First column we will be writing these unknowns C1, C2, C3 that we already know. So substitute those unknowns, you get the output of minus 2x plus x square. And similarly, you find where um, x into 1 minus x maps that I don't know, but I know this can be written as a linear combination of basis vector of codomain space. So that is 1 plus x, 1 plus x square. We don't know what C4, C5, C5 is, but we know the output, we know the matrix of T. So second column will be my C4, C5, C6. So I'm finding the output of T of x into 1 minus x. And T of x into 1 plus x, we don't know what it is, but we know this can be as a linear combination of basis vector of codomain space. So we know the corresponding matrix, third column, that will be my C7, C8, C9. So we know where T of 1 minus x maps, where T of x into 1 minus x maps, where T of x into 1 plus x maps. We will find in general where any vector in a domain space maps. So for any a plus bx plus c square, cx square, we will see where it maps, right? So to find this only, see, the question is reduces to this. You know three output vectors, find in general input. You find for general. Usually we'll solve, right? T of 1 comma 2 is this, T of 3 comma 4 is this, find T of x comma y. This reduces to that kind of problem. So you know T of 1 minus x maps to this. Now this data can be erased. You just have to find a linear map T that takes any input vector to this with corresponding to this, right? So for any a plus bx plus cx square, you take any a plus bx plus cx square in the domain space. In the this a plus bx plus cx domain space, we are applying t to it. So this can be written as a basis. This can be written as a linear combination of basis vector of domain space. So a plus bx plus cx square can be written as a linear combination of basis vector of domain space. So alpha into 1 minus x, beta into x into 1 minus x, gamma into x into 1 plus x. Now we need to solve for this alpha, beta, gamma in terms of ABC. So I'm solving alpha, beta, gamma in terms of ABC. Now I'm applying T on both sides. So I can take T alpha outside by properties of linear transformation, by definition of linear transformation. So we know T of 1 minus x, we know T of x into 1 minus x, we know T of x into 1 plus x. We know all this. So you just collect all the like terms, you'll be getting the general linear map for a plus bx plus cx square. This is a correct linear map because we checked that 1 minus x maps to minus 2x plus x square with this, and also we also checked t of x into 1 minus x maps to 2 plus x plus 2x square. This is the required linear map, right? They are given the matrix because make use of that matrix here to find C1, C2, C3, C4, C5, C6, C7, C8, C9. That reduces to, you know, for three input vector, you know output vectors. In general, you find the linear map for any input vector. That's it, right? That's it. So we are done with this paper. So there are 9 problems. In this question. This paper is very lengthy paper. So you can see almost the solutions are gone up to 2 hours. Okay. So in the next class we will solve 2015 paper. So after completing 2015, we will be doing we will be completing last 10 years of solutions, right? Okay. So thank you. All the best.